Okay. So you should see I posted this morning the Excel assignment. So the first question on the Excel assignment is things we did last class and that we'll do today. The second and third question are going to be things that we probably get to next week. So that due date's pretty far in the future. I think it's I want to say it's something like the 19th. Yeah, so it's a ways off, but I would try to work on that first problem since it's stuff that we've done right now and try to get that kind of ready to go. And then as we kind of get to confidence intervals, then you'll be able to work on that second and third question. Okay, so it's kind of related to what, we'll be using some of the functions that we've already talked about, but the idea of confidence intervals we haven't went over yet. So we'll have kind of the tools in Excel that you would need to do it, but we just haven't talked about that concept of confidence intervals. Other than that, have that connect assignment. That's kind of the due date's a lot closer, so I would start working on that. You have the majority of the material you need to get through most of those questions. And if there's no questions from me, kind of jump into things here today. You guys hear me okay on Zoom and everything? If you ever have any problems, let me know. Say something or type something in the chat if the audio is bad or anything like that. Okay? So, yeah, so the connect assignment here, let's pull this up. So we've got that connect assignment. Let's do what? A week from today? Yeah, so next Wednesday. And then the next Excel assignment would be due even a week from that, right? And that's when I said, I would start working that first problem just because it's going to be things that we've went over relatively recently. And if you kind of hold off on that, by the time you start working on it, you might be like, what was going on here? But it shouldn't be too bad, I don't think, that first problem. Okay? All right, so we left off kind of talking about this normal distribution. How do we take a normally distributed variable, find the probability that's below or above a certain value? We could convert it into a z-score. We could look it up in the table and find that probability. Right? So we're going to do something really similar today, but it's basically like we're working in reverse. Okay? So it's called the inverse transformation. All right? So if we think about, we start out with this formula we have for converting any value for x into a z-score. Right? We're going to rearrange this a little bit so that we solve for x here. Okay? So we have this inverse transformation formula. What this is going to allow us to do is say, before what we were doing was saying, let's say we have a normally distributed variable of rainfall. What's the probability I see less than 1.3 inches of rainfall? Well, we can convert that into a z-score, go to the table, find that probability. Now what we're going to do is say, well, look, what if I wanted to know what amount of rainfall, right? Would there be a 10% chance of me seeing that amount of rainfall or anything less? So now I know the probability that I want, that 10% or 0.1. And I want to find this x value, or this cutoff, that would give me that probability. Or you kind of think about it visually, that area in the tail. Right? So we're really just working kind of backwards. All right, so we'll start with this example, and I'll kind of draw this out and kind of make the comparison to what we were doing last class. So let's say we have this normally distributed variable, and it's the test, some test that was given. And the average is a 72, or the mean is a 72, and the variance is a 64. Okay? What would be the lowest score? What would be the cutoff for that top 10%, right? Or what score could I get that would put me right at kind of that top 10%? Okay? Well, we can use this formula and work backwards, right? So I know the mean, and know the standard deviation, right? If we have the variance, standard deviation is just the square root of that, okay? So I can plug those two values. Now I need to know the z-score because I'm looking for what that cutoff value is for the top 10%. So how can I do that? All right. So if we think about what we're doing here, we have this test score variable x. It's normally distributed. It's got a mean of 72, standard deviation of 8. You think about, we can convert any normal variable into a standard normal variable, or z values. And what we know is we want the cutoff, right? We want this x value such that the area to the right of it is 0.1, right? Or 10% of the other scores would be higher than it. Right? So another way to think about this is, if the area to the right is 0.1, what's the probability to the left? Well, the area under the curve is 1, so just 0.9. Right? So we know that for whatever this score is, we don't know what it is yet, but we know that if we could convert it into a z-score, we would want the z-score that would have an area to the left of it of 0.9. Well, we can do that. It's just using the table a little bit different than we did before. So let's go back here. I'll pull up the table. Okay. So before we had the z-score and we were finding the probability of seeing that z-score or less, or the area to the left. Well, now we know the area to the left, or we know the probability, and we want to find what z-score corresponds to seeing that probability in our tail, or that area in our tail. So I'll look through here. Here's all my probabilities, right? Well, I want 0.9, so I got to go up quite a bit. Oh. Hold on, let me make sure that was, I think that was related to the PDF. Okay, we're still going here. So I'm looking, what's close to 0.9? Looks like these two values are the closest I can get to that probability of 0.9. So I know that the z-score that would give me approximately 0.9 in the tail would be 1.28 or 1.29, right? The z-score should be somewhere in between there. Well, I'm kind of limited to 2 decimals here. So anytime we're in between 2 z values, we'll just choose the higher of the 2. So if we're in between 1.28 and 1.29 here, we'll use that z-score of 1.29, okay? Yeah, we're limited by this table, and so that's kind of the convention we'll use for this class when kind of coming up with answers, right, or solving these. Now, I'll show you eventually in Excel. In Excel, we're not constrained. We don't have to worry. We can get the exact z-score. We can get 1.283475, right? So we'll use that 1.29. That's that z-score we were looking for. Well, now it's just a matter of kind of working reverse. We had that inverse transformation formula, which we needed the z-score, we needed the mean, and we needed the standard deviation. So now we have everything we need. If I can be a little bit quicker here, right, to plug into this formula, okay? So we found that z-score, right? We'll plug in those 3 values, and we'll get the cutoff score for the test score. That would give us kind of 10% of the scores above it would be 82.34. And that makes sense because if we were thinking about we wanted only an area of 0.1 to the right or an area of 0.9 to the left, well, that should be something that is above the mean, right? Because the area to the left of the mean is 0.5. So if I want the area to the left to be 0.9, hopefully I'm finding a test score that's greater than the mean, right? Sure enough, I did, right? Now, another way I could have done this, instead of using that inverse transformation, let me see if you guys can see this on this. I could have just used the formula for the z-score, right? Which was x, subtract the mean, divide by the standard deviation. Well, standard deviation was 8, mean was 72. The z-score that I looked up was 1.29. And now it's just a little bit of algebra, right? Now I could have used that inverse transformation formula. It was already kind of in a better format for me. But really, I could have plugged into that z-score formula and kind of done a little bit of algebra as well, right? Just a little bit easier if I do the algebra first and then plug everything in, okay? Any questions on that? Is that making sense? Okay, we'll go through another example here. So let's say instead, I get the same sort of setup, but now I want what score would kind of give me that bottom 40%, right? Or what score would there be a probability that I see that score or lower, probability being 0.4 or 40% right below it, or 60% above it, right? So we want the bottom 40%. Well, right away, right, if we think about this, I got the same sort of setup, but all right, here's our test score. It's normally distributed, mean of 72. But now I want, what's the test score that would give me 40% below it, right? Well, right away, I know that this test score has to be less than the mean, because the area to the left of the mean is 0.5. So I know I'm going to be looking, hopefully when I get to my final answer, I'm going to see a test score that's less than 72, right? So if we look at even the possible answers there, we can rule out B right away. If we're thinking about a test score, A doesn't really make sense to have a negative value. And 0.26 seems like it's way below the mean, right? If the mean is 72 here and the standard deviation is 8, then to see something that was a test score of 0.26 would be way over here. That area to the left would be pretty close to 0. So right away, we could probably rule everything else out and figure out it was what, 68 or 69 point something. But let's just work this out completely in case there was other answers that did make sense. Okay? So what we know is that if we can had this x value and we converted it into a z-score, that z-score would have an area of 0.4 to the left of it. So we'll look up that probability we want of 0.4 in the table, get that z-score. We then have everything we need for that inverse transformation function, or sorry, not function, formula. We'd have the z-score, we'd have the mean, we'd have the standard deviation. We could plug them in and figure out what test score would give us that 40% below, or be the kind of the cutoff for the 40th percentile. You want to think about it that way. Okay. So we'll go to that table. Just pull it up here. We want the area to the left to be 0.4. Well, these are too high. All right, here we go. Looking pretty close, in between these two values, right? So negative 0.2, scroll up, 5, and negative 0.26, right? Now we have negative values. When I say take the higher of the two, it's actually like the highest absolute value, right? So between negative 0.25 and negative 0.26, we'd use negative 0.26. Okay. So we now have that z-score that we wanted, negative 0.26. We'll use that inverse transformation formula, which is take the mean. Now, we're adding the z-score, but if the z-score is negative, right, we're subtracting, and then times whatever the standard deviation was, which was 8. Okay. We compute this. Like I said, I think we get, what, about 68 or 69. Let's see, I get the actual value here in the slide so we can kind of complete this, all right? All right, 69.92. All right, we plug everything in there. Now, notice I wrote this here as the square root of 64. So, if I wanted the standard deviation, that was just the square root of variance. We're typically given the variance, and so that's why I have it written out like that. It's probably easier, for the video, let me close up. It's probably easier to just start out and find your standard deviation right away, right? That's that's what I would suggest doing. When you're given that variance of 64, right away, take the square root of that and figure out that your variance is 8, right? Now you can just kind of plug in the standard deviation there, okay? Any questions on that before we keep moving? We okay with that? So if you have a probability and you want to find the z-score that gives you that probability, you're going to look up that probability in the middle of the table and then go up to your row and column headings to figure out what z-score corresponds to seeing that area in the tail. If you have the z-score and you're trying to find the area to the left of it, or the probability of seeing that or anything less, you use the row and column headings and then get that probability you want. Right? So it's just working kind of in reverse there, or inverse, right? So let's go back to that Indiana weather file. I have this inverse transformation worksheet, right? And I've got a bunch of stuff in here. I'm going to delete it real quick. Just kind of show you how we can recreate this, right? So I've got my mean of that test score. I've got that variance of my test score, right? if I want to find what's the probability that the test score I see, if I want to find what's the probability I saw the test score that I did for X or anything less, I don't know what that test score is, but I know that's going to be the cutoff for that top 10%, or we said the area to the left being 0.9. I can use a formula in Excel called norm.INV. Okay. I tell it, all right, well, I know the area that I want to the left, so it's just like we're using the table. The area I want to the left is 0.9. My mean is right here. My standard deviation, well, here, I only have the variance, so square root of the variance, okay? And then that's all I need. What this is going to do is it's going to go to the table and say, okay, I want the area of 0.9 to the left. I'll look that probability up in the table, find the corresponding z-score. Once I have that z-score, I'll use that z-score, the mean, and the standard deviation, plug it into that inverse transformation formula, and spit out, right, and Excel spit out at us what the test score would be to get that cutoff where 90% was below it, right? Or an area of 0.9 to the left. So it's going to do kind of all the work behind the scenes for us, okay? Sure enough, we get that same test score that we found of 82.25. Now, if you look at the slides, there we go. Where was it? There it goes. It's a little off, right? So 82.34 is what we got if we did it by hand. But Excel can be exact. When it goes to the table, it doesn't have to say, well, the z-score is somewhere in between 1.28 and 1.29. It uses the actual z-score of like negative 1.28. I don't know what it ends up being, right? And so we're going to be a little bit more accurate if we use these formulas in Excel, okay? Because we're not constrained to using 2 decimals like we were in the table, right? Now, the alternative way of finding it, kind of like when we had the norm.dist and the norm.s.dist, right? We could have first said, okay, what's the z-score that gives us that area of 0.9? Well, we're looking for a z-score, so we know we're dealing with the standard normal distribution, so norm.s.inv. All we have to tell this is, well, I wanted the area of 0.9 to the left, and it's essentially going to go to the table, look up that probability of 0.9, and spit back out at us the z-score that we need to plug into our inverse transformation formula. Now, we were in between 1.28 and 1.29. Notice Excel can give us the exact z-score. So 1.28155. Right? Now that we have that z-score, it's essentially using Excel as a calculator, right? So our inverse transformation formula was, take the mean, add to it the z-score times the standard deviation, which here all we have is the variance, so we'll have to multiply by the square root of the variance, right? Okay. If we do that, sure enough, we get the exact same answer, right? So this way, we're actually able to see what that z-score is. But if we don't care about what the z-score is and we just want to know what's that cutoff for the test score, right, that value for x, we can kind of skip the intermediate step and just use that norm.inv function, okay? Any questions on that before we keep moving? And I'll leave that up here for a second. So, even if we weren't dealing with an example like this, you could actually use this norm.s.inv to start looking up z-scores instead of using that actual table, right? And you can get a little bit more exact, right? You're not constrained to 2 decimals. Okay? If I had this set up too, if I change some of these values, instead of putting 0.9 in here, let's say I'm interested in that probability. So instead of putting the number in, I use a cell reference. And now I want to change, okay, what would be the test score that's the cutoff for the bottom 40%? So the area to the left is 0.4. Now it'll update it for me. And we get an answer very close to what we found by hand, right? A little bit off because we're not constrained to 2 decimals. Okay. Any questions on that? I'm going to see this again. All I did here was change that 0.9 to the cell reference where I had this probability that could change from 0.9 to 0.4. Okay. Now, I'm going to ask you a question here. If I change this probability to 0.5, what should this give me? Yeah, right? It should give me exactly the mean. Sure enough, it returns me exactly the mean, right? Because I know the area to the left of the mean is 0.5, okay? All right. Any questions before I kind of jump out of Excel here? Want to see something again, or we're okay with this? Okay. All right, so here's kind of a nice little reference here. I'll work through one more example because I think it's a little bit fun before we kind of, well, I'll say this for the end of class. We'll jump into something else. So we'll start here, this random sampling slide. And we're going to kind of take a little bit of a step back away from the normal distribution for a second and talk about when we collect data, what are some biases that could exist in our sample? We're using this to set up eventually something we're going to talk about, the distribution of sample statistics, right? So all of the kind of behind the scenes, when we're talking about that normally distributed variable, we're assuming that we're looking at a population, kind of the population, right? We can't usually do that. We don't have the population mean, right? If I look back here, I don't have, if I can do this, oh my gosh, okay. I don't have the population mean. I don't have the population variance usually. All I have is sample data. So when we're dealing with samples, we want to make sure those samples are reflective of the population as a whole, right? Because if they're not, right, if I'm interested in, say, the average income in the US, but I only sample people who are between the ages of 18 and 24, well, that average income is going to look way different than the populations, right? So, we have two kind of scenarios, either a finite population or an infinite population. Everything we're going to be dealing with, we're going to be thinking about it's finite, right? I'm usually talking about average income in the US. Well, that's a finite population, right? There is a certain number of people in the US, right? Infinite is, an infinite population is usually some data generating process. We're not really going to be dealing too much with this in this class, okay? Now, we talked about a long time ago, the very beginning of class. It's not feasible usually to get a census to get population data, and so we're usually stuck with a sample. So we want to make sure the sample is reflective of the population as a whole. So some of the notation that we've already been familiarized with is, my population size is capital N, my sample size is this lowercase n, right? So I want to make sure when I'm choosing the sample that, well, first that we can do it with and without replacement. More often than not, which of these do you think we probably want to use? So with replacement would mean, let's say I was sampling from this room, sample 5 of you guys, right, out of the entire class. If I do it with replacements, that's like I have everyone's name in a hat. I draw someone's name out. Maybe I'm looking at height. I record their height. I put their name back in the hat. I then draw out another name, record that person's height, put it back in the hat. So that'd be with replacement. Without replacement would mean if I take someone's name out, I write their height down, I don't put that one back in the hat before I make my next selection. So which one do you think we probably want to use more often than not? Without, right? Because theoretically, I could end up choosing the same person's name all 5 times. Well, now that person is, one out of whatever the population is, as opposed to having 5 different people, right? So more often than not, we're going to, want to use without replacement. There could be some scenarios where we want to use with, but for almost everything we'll do from here on out, we're thinking about doing this sampling without replacement, okay? So we do this without replacement sampling. I randomly sample however many people I want in my sample, lowercase n. And I can start to think about how I still might have some issues, okay? So first of all, I need to make sure that every single person I was sampling, every element or every observation I'll end up with in my sample data set comes from the population I'm interested in. If I'm looking at the average US income, I don't want to randomly select somebody from Canada, right? Okay, so that one's pretty easy. I want to make sure that these randomly selected people are independent. So I can give you an example how this might not happen. Maybe I'm calling people like to survey. I finally get someone to respond. And so then when I get them to respond, I say, well, can I ask someone else in your house to take the survey? Well, if we're talking about families and they're living together, it's likely that they have characteristics that are similar. So now those aren't independent events, right? But never going to try to trip you up on these. Most examples will talk about this criteria is met, okay? So we'll talk about a couple strategies to make sure that even when I'm randomly sampling, I can end up with samples that I can guarantee are more reflective of the population than if I just completely randomly sample. So the first is going to be called stratified random sampling. So I'll divide the population into a bunch of non-overlapping groups. I'll then randomly sample maybe 5 people. So let's set it up this way. Let's say I've got my population. Right? I'll then, maybe I'm looking at the US, I divide it up into regions of the country, right? Or even states. Right? We can do states. If I want a random sample of 100 people, but I want to make sure every state is represented, right? Or equally represented. So what I might do is randomly sample 2 people from each state, and then once I have the random 2 people from each state, put all of them into a data set, so I now have 100 random observations. They weren't completely random because I want to make sure I had 2 people from every state in that final sample, right? That's the idea of stratified random sampling. Because if I divide this up by state, they're non-overlapping groups, right? You can't kind of be, well, we'll say your primary residence can't be in 2 states at once. I guess maybe if you were built on the state line or something, but I'm guessing they're not going to let you do that. Right? Excuse me. So the process I described there was I created these stratum, right, or non-overlapping groups. I then randomly selected from each one of those non-overlapping groups, and then combined them all to make my full sample. Okay? Now, the state one might not make a whole lot of sense for a lot of examples, but I'll give you a better idea. It's not that we have to equally random sample from each group. Maybe I want a final sample of 100, right? But I want to make sure that that has every kind of age group represented that matches the population, right? So if we look at the number of people who are between 70 and 80, there's fewer of those that exist than the number of people between 20 and 30. So maybe I divide this up by age groups. I randomly sample maybe 20 people between the ages of 20 and 30, maybe 16 between the ages of 30 and 40, 12 between the ages of, so on and so forth. And then I throw all those together to get my full sample. Now I know that my sample, if I chose those numbers to kind of match up with the demographics of the population, now I know my sample looks just like my population in terms of age distribution, okay? I might want to do the same thing, based off of any other characteristic there that I think I want to make sure my sample matches the population. What did I say here? I think I gave some examples, age, gender, maybe income distributions. I want to make sure that my sample matches kind of the income distribution of the population. So I break it up into randomly sampling people who make between 20 and 30,000, 30 and 40, so on and so forth. Okay? So if I just did completely random sampling, especially if I'm doing a small sample, let's say I randomly sample 10 people, I could end up with 10 people who are all maybe the same gender. Well, that might not be, it doesn't match up with my population at all. We know the population is about a 50-50 split, right? With higher sample sizes, I might not be as concerned, but this kind of would guarantee it no matter what sample size I want. Cluster random sampling is really kind of the same idea. The only difference here would be we're kind of breaking the population up into subgroups. So this one's probably, I'm not going to like quiz you or make you kind of identify the difference between cluster or stratified random sampling. When I use the state example, that might be something we think of more as cluster. If we thought each state kind of looked the same, we know that's probably not true, right? There's states differ on a lot of characteristics, but maybe I'm interested in something like average incomes in large US cities. So there, maybe I cluster random sample and break it up because I think each city is like a representative subpopulation of the entire set of large cities, right? And so maybe I randomly sample 10 people from New York, 10 people from LA, 10, go down the list, and then I throw those into my full sample, right? So it's really just the same exact idea. It's just that it's more so we weren't breaking people up by characteristics. we were thinking about, we were just breaking it up, and these are just different subpopulations. There's no reason to believe that these subpopulations might be wildly different in terms of the characteristics, but we know that each one kind of gives us a small scale version of whatever the entire population we're looking at is, okay? So cluster and stratified random sampling, very similar ideas, right? And like I said, I'm not going to focus too much on those because I'm not going to try to trick you or ask you the difference between the two. So I'll go through an example and we can start to think about how we might apply this. So let's say I was wanting to do a political poll, right? So what proportion of people are going to vote for a specific candidate, right? Well, if I just randomly sampled this and I somehow ended up with an overrepresented number of people from the South, right? Well, we know the South is predominantly kind of leans more towards one political party, and so my sample is not going to be reflective of the population as a whole, right? So what I might want to do is kind of break this down into different regions of the United States, randomly sample maybe 10 people from each one of those regions, then throw them all together to get my kind of full sample, right? You know, so the idea here is we can't get population data. We're stuck with just a sample. Let's make this sample as best as we can, okay? So what could go wrong? Even if we do this stratified random sampling, cluster random sampling, we make sure that the characteristics of our sample look very similar to the population. We still could have a bunch of biases that exist, and we'll kind of set this up with an example. So in, 36, Alf Landon was the other guy running for president who lost to FDR, okay? So first of all, I didn't learn this in history. I didn't take a lot of history classes, but Alf is an amazing name. So in that election, prior to it, there's this little thing, my grandma used to get these. They're like these little books. It's like the Literary Digest poll. And they sent out to their kind of people, they built this data set and randomly sent out these 10 million survey cards, right? So they got 2.5 million responses, right? That's really good. If you've ever done anything with surveys or you've talked about in other classes, a response rate of 25% is amazing, right? Most of the surveys I get, if I have a phone call, I hang up right away. If it's something in the mail, I throw it away, right? So they got 25% of people to respond. And it predicted that in a landslide that Landon was going to win 57% of the popular vote, and then the electoral vote, kind of when they looked at where people were coming from, was going to be also kind of a landslide here, right? Well, clearly we know that didn't happen. FDR was the president. In fact, it was a landslide in the opposite direction, right? He won 523 of the electoral votes, which is crazy. I think it's maybe not the most. I think there was one more, some other person that won more, but that's a lot, right? So what went wrong? Why did their sample of 2.5 million people, right? How was it so far off? Well, what they did, well, this is just me being stupid, right? Did they make mathematical errors, use the wrong formula when calculating their variances, only send the mails, or only mail these postcards to Republicans? Well, that could have swayed it, right? If for some reason they did that, well, they didn't purposefully do that. Were Republicans more likely to respond? So even if I sent 5 million mailing cards to Republicans, 5 million to Democrats, if not a single Democrat responded, but 2.5 million Republicans responded, well, now my sample doesn't reflect the population. What actually happened is we had two biases that existed within this sample. And we'll talk about in the context of this example in a second, but more generally, we have a selection and a non-response bias. So the selection bias would have been if they, sent all the mailers or a larger majority of them to Republicans, right? They're selecting more of one group than another, right? And we know that in general, the breakdown of the population in terms of political parties is about 50-50, right? That's why we continuously swing back and forth between different political parties as our president. The non-response bias would have been if one of those parties just wasn't as likely to respond, right? If there's some systematic differences in certain groups, that some groups are more or less likely to respond, okay? So we can kind of see if this happened with what they did. So, the biggest problem with what the Literary Digest did was the way that they got this list of 10 million people was that they, sent it out to people who had either a telephone at the time, so they're using telephone books, but they had to have a telephone and their name had to have a car registration with it, right? If this is 1936, what kind of people own cars and telephones? People with money, right? And we typically know that if we look at on average, higher incomes tend to kind of vote more right or vote more Republican. So right away, if this is how I'm getting my names, I'm going to have a selection bias. I'm over-selecting wealthier people that tend to be Republicans. So more of my mailers are going to be going to Republicans than they are Democrats, right? So right away, I'm going to have this selection bias built into my sample. So if we look at the actual data, there was this paper that came out, I forget, when it was somewhat recently, and not in the 30s, like, last 20 years. And they were able to kind of track down a lot of these people that were originally surveyed and kind of look at who did they actually vote for, right? And so if we look at people who owned cars and telephones, right, at that time, 52% of those people actually voted for Landon, right? So if I oversampled people who had cars and telephones, it's going to lean me more to thinking that Landon would have won, that right-leaning candidate or the Republican candidate would have won. And if I break this down by not just owning both, but owning only one of them, I wouldn't have, they made, their sample, you had to have both. If they would have only chose that you only had to have a car, well, even then, if you only own a car but not a telephone, 60% of people who only own a car are going for Roosevelt. And a lot of this has to do not just with money, but at the time, telephone lines were more likely to be seen in bigger cities, right? And so if they only owned kind of a telephone, maybe we had, if they only owned a telephone, we still had, it would have looked like Roosevelt won. But because they chose their sample based on needing to own both of them, they predicted that Landon was going to win, right? And if we look at people who own neither, even higher percent of them ended up voting for Roosevelt, okay? So we had a definite selection bias here, right? What about the non-response bias? Well, it wasn't that only, right, Republicans responded, but when we look at the breakdown here as well, it didn't matter if you owned a car and a telephone, only a car, only a telephone, or neither. If we look at what was the likelihood that the people responded to this survey, well, if they owned a car and a telephone, if they were going to vote for Roosevelt, only 17% of people responded to the survey. But if they were going to vote for Landon, for some reason, 35% of them responded to the survey. So for whatever reason, there was an over kind of response from Republicans as opposed to Democrats. So they didn't, there's nothing that the Literary Digest could have done to prevent this, right? Because people just send you back the mailers, right? But they have a non-response bias here as well, right? Roosevelt voters were just more likely not to respond. And if we actually look at, no matter if we would have just chose it by car only, telephone, or neither, kind of notice Landon, the people who were going to vote for Landon were always kind of more likely to respond to this survey, okay? So how would they have prevented this? I doubt they knew this ahead of time. I'm not sure exactly. I forget what the article I think the article talks about maybe what was driving this is people with lower incomes tend to have less time to respond to things. Maybe they're actually worried about going out and working, making more money, and so maybe they're just less likely to respond, or they're less likely to be involved in politics, so they're less likely to send these surveys back. But this is a nice example, I think, that really gets at these two biases, selection and non-response biases. Okay? So we'll talk about a few more examples before we end class here today. And also another type of bias we can have is that people just don't tell the truth. Now this can be malicious or non-malicious, right? And the idea of a political poll, I might non-maliciously lie to you. Maybe at the time of the survey, I was going to vote for one candidate, but when actually election day got here, I changed my mind. That's a non-malicious lie because you now have inaccurate data. I didn't mean to lie to you. It's just I changed my mind, right? Now you could maliciously lie. I think, maybe in current political environment, maybe if you ask somebody who they're going to vote for, even if they know, maybe it's not, they don't feel it's like socially accepted, they might just tell you the other candidate, right? And so we have non-malicious and malicious lying that we can see as well. We've got kind of this newer idea that you look at how things are phrased. Maybe people misunderstand the question, or they read the question and different people will perceive it a different way. I saw something last election about, it was the same, I think it was, it might have been Fox or someone, but they asked two different questions that really were like the same question, but just phrased differently. Like one of them set up, do you think that President Trump is doing a bad job, and the other one said, do you think that despite all of the difficulties, President Trump is, like not doing the best job he could, right? And so just the phrasing in which they asked that, they got very different responses, right? So just the way the question is asked can also kind of build in a bias, okay? So I always have these examples. Usually I go through the clickers and we look at like everybody's responses, and it's kind of interesting to see the biases that exist, even in these really simple examples, right? So the first one, I might ask the class, how would you rate your health today from 1 to 4? Everybody responds. We look at this. A lot of the times it's, averages around a 2. And then say, okay, what biases could be built in here? When we think about the selection bias, right? If I didn't tie points to it, maybe people who are healthier would be more likely to respond, right? If I don't feel like I'm as healthy, maybe I don't want to respond to that question. And so I might have a kind of, not a selection bias, a non-response bias there, right? Because the healthier people would be more likely to respond, right? Now, if I looked at a class, I looked at you guys, I had all of you in person here, what would my selection bias be? Well, if I'm interested in the health of the entire country, hopefully, right, you're at a younger age group, I've over-selected young people, it's likely that the sample mean I see for health here would be much higher than the population as a whole, right? Because we don't have any 70 or 80-year-olds in here, right? We should kind of drag our mean down. Okay? Maybe people would lie. Maybe people don't want you to know they don't feel like they're in as good as health, so they might maliciously lie here. They might non-maliciously lie because they read the question real quick and they think 1 to 4, oh, I feel like I'm in good health, I'm the highest, I'm a 4. No, the way that the question was set up is actually the lower value meant better health. Right? So you can see all these biases existing, and even a simple kind of question like this. Right? We got 7 minutes thinking we can work through this. So I kind of put all these points here. Another one that could exist that we didn't really talk about, but even having these discrete options, if I can only go 1 through 4, but I feel like I'm a 1.5, you've actually forced me to lie to you. Because I have to say either 1 or 2. Now, not maliciously lying, but I have to tell you 1 or 2, and that's not exactly how I feel. So my data won't be really representative of how that person actually felt their health was, right? Because I forced it to kind of be discrete here. Now, we're dealing, kind of mentioned, we're not really dealing with discrete variables anymore. And so we're going to be dealing with continuous random variables. So in most examples we look at, we're not going to have to worry about this bias. I always ask this one too, how many alcoholic drinks do you have on average? And I always say, if I had you guys respond to this, right? First of all, my non-response bias might be that if you feel like your number's high, maybe don't want to respond to this at all. Or I don't know, maybe for social pressures, if you feel like it's 0, maybe you don't want to respond for that. If you think that I'm going to look at the data, right, and you're not 21, maybe you don't respond because of that, right? So I have some non-response biases built in there. Selection bias, if I'm choosing a room full of college students and I'm worried about the alcoholic behaviors of the country, well, my selection bias, I over-select the young people, I'm probably going to see a much higher mean than if I look at the country as a whole, right? So I've got selection, non-response biases built in there. If you're not 21, you might lie to me and say 0 if you think I'm going to look at the data. There's always the person at the party who wants to brag how much they drink. So maybe people are maliciously lying and saying greater than 12. Maybe, we could kind of think about there's a lot of different lying biases that could be built into a question like this. Right? You could look at this, well, on average, who keeps track, right? So I might tell you the number I think it is, but it might be a little off. So I'm not maliciously lying to you. So all these types of biases are built in, and whenever we look at a sample data set, we want to think about how is this collected and how might it not be representative of the population as a whole. Okay. All right, so I just kind of lay these out. I kind of want to work through that example today, but where are we at? Let me see how much more I have. Well, got 4 minutes, so I'll go through this because I think it's kind of interesting, and we'll do the other examples on Friday. So we're getting close to the election, and I had this set up from last time. Actually, on Canvas, I'll put up, I have a couple articles that kind of line out these next points. We can think about in the last election, there was all these polls that got it wrong. There's only like a couple, I think 1 or something that got the prediction right that Trump was going to win. So how'd they get it all wrong, right? So if we think about selection biases, if we're thinking about political polling, If it tends to be in larger cities, or I'm just more likely to get people to respond from larger cities, then I might have had a selection bias built in. But these articles were trying to survey people after the election and try to get at this idea that there likely is a huge non-response bias in political polling. I think the article argues that it's because Trump might be a divisive figure and there's some social pressures, right? So who might not be likely to respond? Well, the article calls these like shy Trumpers, right? People who knew they were going to vote for Trump, but didn't want to respond to surveys and say that they were. So there was a lot of people kind of, when we think about not responding to these polls, even though they knew who they were going to vote for, or saying they were undecided, even though they knew who they were going to vote for. Right? Intended lying or unintended lying. Maybe there was a lot of people who changed their mind in between when these polls were taken and when the actual election occurred. And then the malicious lying is also, they kind of blame these shy Trumpers, people who knew they were going to vote for Trump, but when asked to do so in a social setting, aren't going to say they're going to do that, right? And so I'll post those up on Canvas because they're kind of interesting, and it kind of talks about how we might want to rethink about how we do political polls, specifically making sure there's some anonymity to it. So a lot of I used to, when I was in college, I did a phone bank once to call and see who people were going to vote for, like do a survey. And maybe moving from that to something like electronic, where you can't actually there's no real personal connection, right, when you're trying to elicit this response from the person. So I thought that was kind of interesting, just kind of fit this bias discussion we're going to have. I'll pick up on Friday with another normal distribution example that I think is kind of interesting, and then we'll get into this idea of, if I have a sample, what does the distribution of my sample means look like, okay? And then I'll leave you with one meme that I think is funny that I skipped over. Maybe use this on if you're still going out on the weekends. So if hotness was a normal distribution, you'd be 3 standard deviations above the mean. Obviously, you would change this to that you're a z-score of 3, because then if they don't understand what that means, then you know they're not smart. All right, well, we'll leave it at that. Look at that Excel assignment. Try to get it started for problem 1. And I'll see you guys on Friday.